Okay, welcome to class. Hello, hello. Nothing? There it goes. Hello, hello, hello. Hello, hello, hello. There it is. Okay. Okay, welcome to class. We have a demo we're going to start with, and we have to act kind of quick because it won't work if we wait very long. And as it is, we only have a 50% chance of it working. In the 4 years I've done this, it works 2 times. Today we're going to move that up to 60%, I hope. Okay, what I have here in this cooler is a bunch of Fiji water bottles, which I put in the freezer last night. So you'd expect if you put some water bottles in the freezer 12 hours later, whatever it is, they should be good and frozen. And some of them might be, some of them are still liquid though. So what we're going to do is I'm going to take one of these. Okay, this one's solid, that one's ice. This one is still liquid. You see that bubble moving? See that bubble? Put it down here, right? Definitely still liquid. What I'm going to do is I'm going to give it a hit on this table. See that now? See how that's moving through it? It's freezing before your very eyes, right? Let's do it again. This one's already frozen. You don't have great success rate with this. That's why we put like many in here. That one's frozen. This one's liquid. On this one, I'm going to take it out and I'm going to carefully try and take the lid off. I'm going to pour it into this bowl.
Is this because it's Fiji?
Magical. Okay, hopefully. Okay, what I'm going to do now is I'm going to pour it into this bowl, and it should kind of turn into a slushy as it hits. Sometimes it works, sometimes not so much. No, that one's just water. That one's not cold enough. Boring. All right, let's try another one. Boo, the hecklers. Let's try just one more. This one's clearly still water. Let's just try and watch this again. So again, I'm going to try and show you a clear side. When I whack it on the table, see those ice crystals in it? They start to crystallize, and they'll start to grow, right? It may not be quite cold enough to do the pouring trick. Okay, so that's our example of supercooled water, where, you know, we gave it some sort of driving point. Now this turned into clearly ice inside of there. It's not like a really hard ice. It's like a slushy ice, but it is definitely ice, and it was definitely liquid moments before. Okay, that's an example of homogeneous nucleation, right? This bottle, it's DI water, meaning it's distilled water, right? So they've taken out a lot of the ions in it. Those ions serve as lower energy nucleation sites, right? As we're going to talk about today, we talked about homogeneous nucleation where little spheres form in the middle. That's basically what you saw. You saw when I hit this, like little stars sort of formed in the middle and they grew out from that. That's homogeneous nucleation. The opposite of that is heterogeneous nucleation, which you've all hopefully seen, and if you haven't, we're going to do it today. Christian has a Diet Coke over there. We have a little Mentos launcher thing, and we're going to drop them in and talk about the difference here. It's a good idea. It's a good idea. And if you notice these drip marks on the ceiling, it's from this demo. Hold on, just wait 1 second. Oh, now I did it. Unbelievable. What did I do? Hold that thought.
You can hear that?
Should have. Okay, hold that thought. We keep that at the top. Okay, here we go. You have the Christian. Okay, there it is. Here goes. Okay, fantastic. Fantastic. Yeah, you can use this. Okay, so let's describe the difference between the two things that we just saw. On one hand, what was the reaction that happened with the water bottles? What's our reaction? Liquid water into solid water. Or in other words, when we are in a freezer, we're below 0 Celsius, there is now a free energy thermodynamic driving force for it to turn into a solid, right? However, there was this surface energy that gets created, and so to counterbalance that, you can actually go below that temperature. When you hit it, it starts to, you basically provide enough energy for it to overcome that activation energy, and it crystallizes. On the other hand, what's our reaction over there with the Diet Coke Mentos? What happened there? What's the chemical reaction or the reaction that happens there? Is it Matt?
Yeah, I actually have a question.
Yeah.
Why did some of the Fiji waters freeze already and other ones weren't frozen yet if they were all in the same place?
Great question. Let me come back to that. Okay, I'm going to come back to that in just a minute. Okay. What's the reaction happening with the Diet Coke Mentos? Yeah, Jeff?
Carbon dioxide is coming out of solution.
Yeah. Most people think that this is a chemical reaction, that it's like, I don't know, the sugar in the Mentos is reacting with something in the Diet Coke or something. That's not what's happening at all. What's happening is that in any carbonated drink, you can make this work to some degree. It works great with Diet Coke for other reasons. But anytime that you have a drink where you have CO2 that's dissolved into the liquid, right? How they do that, they just pressurize the liquid with a bunch of CO2 until it dissolves into it. That gas wants to come out. That's why if you open the top of a Diet Coke, it will get flat over time, right? Flat soda is one where the CO2 has left it. So all that we do with the Diet Coke Mentos is we add Mentos, which adds really low energy nucleation sites for those gas, dissolved gas molecules to turn into vapor gas, right? And in doing so, shoot gas all over the place and soda all over the place, right? So why does it do it versus other things? One reason is that Diet Coke has a aspartame. It has the artificial sweetener. Some people have argued that that is changing the surface energy. We know that this is all a competition between free energy and surface energy, right? You've got these two terms, and by adding this artificial sweetener, you change this surface energy term. And why does Mentos work particularly well when things like, I don't know, we tried a bunch last year, Smarties and all sorts of other things, they don't work nearly as well? The reason why is if you zoom in with an electron microscope on the surface of these Mentos, they actually have a surface that looks like this. Instead of like a nice round candy, it's actually filled with tiny little pock marks, right? And each one of those serves as a nucleation site, a low energy nucleation site for the gas. So back to Matt's question, why did some of these bottles, they were ice already and some were still liquid? So we'd like to explore homogeneous nucleation, but because of that, you have to have water in some sort of container, and there might have been impurities in the bottle. There might have been slight different temperature differences in this itself. We put this inside the furnace because if you take one of these and set it right on the bottom of your freezer, it's going to be in contact with the bottom of that, which is usually far colder than what it's designed to be in the middle of the furnace. So we put it inside of this at room temperature so that the cold would slowly diffuse into it rather than the heat would slowly diffuse out. But some parts might have gotten colder than others, might have been flaws in the bottle, might have been defects in the water, right? Any of those things could have been it. Okay, any questions about this so far? Heterogeneous versus homogeneous nucleation? Yeah, Rosa?
Is this something similar to the reason why if you heat up some water sometimes it does boil and you move it and explodes?
Exactly why. So we talked about that at the beginning of class last time, where if you put it in a really smooth coffee mug, a bunch of water, and you boil and you microwave it, and you don't see it boiling, so you think, oh, it's not done yet, and you keep on microwaving it, and it just doesn't do anything. But then you take it out and you put your spoon or the tea bag or whatever inside of it, and it shoots steam everywhere, and it starts to rapidly boil. It's the exact same phenomenon. It's just a different reaction. In that case, you've got water molecules, which are in the liquid state, which want to turn into the gas state, but in doing so, they're going to create bubbles, which have surface energy. Exact same phenomenon, right? Yeah, in the back, Spence?
What is the difference between the homogeneous and heterogeneous?
Let's talk about that today. That's a perfect question. So today's learning objectives, first off, we're going to derive critical nuclei size and the nucleation activation energy for heterogeneous nucleation. So we'll describe what's the difference, basically. Why do they have a different activation energy, different nuclei size, right? Do they have a different nuclei size? We will then talk about how you can model transformation by taking into account both growth and nucleation, right? So the total transformation, you have to nucleate a phase, but then you have to grow it. And both of those terms can slow down your total transformation. We'll talk about the microstructure of some metallic alloys when you melt them and then cool them down. If we have time, we'll get to Avrami equation to talk about the transformation kinetics. And if we really have time, we'll start into TTT diagrams for steel, which is how you get lots of different steel microstructures by quenching it under different conditions. So let's start where we left off last time, which was with the clicker question we meant to do, right? The clicker question that I asked you guys, we ended up doing, we calculated the activation energy for gold when it's 230 degrees below the point where you expect it to solidify. Now let's do the opposite. Let's calculate its critical nuclei size, right? So not activation energy this time. Oops. Now we're going to calculate R star. That's our first clicker question. Sorry. Our first one, sorry about the reading quiz. First clicker question is the following. It says, in nucleation, a cluster of atoms with a radius less than the critical radius will A, continue to grow with decreasing free energy, B, continue to grow with increasing free energy, or C, shrink and dissolve. Okay, answers in. Okay. What happens, A, B, or C? Definitely C. If it's not yet to the critical radii size, it's going to just dissolve again, right? Next question. The martensite transformation differs from austenite to pearlite or austenite to bainite in that A, it does not rely on carbon diffusion, or B, it does rely on carbon diffusion. And even if you haven't read yet this part about martensite, you should be able to answer this because you know that austenite to pearlite, which is a mixture of cementite and ferrite, either does or doesn't involve carbon diffusion. Okay, so answers in on this one. Okay, I'm going to wrap this one up. Okay, pretty split on that one. This one does not rely on carbon diffusion. When you had austenite, that had some mixture, intermediate amount of carbon, And when that turns into ferrite, ferrite has almost no carbon, and cementite has lots of carbon, so that has to have carbon diffusing. Martensite is different than that. We'll talk about what it is later today, if we have time. And then the last one here is, what will be the hardest steel alloy? Which of these microstructures is the hardest? Is it spheroidite, martensite, perlite, or bainite? Okay, answers in. Gonna wrap it up. A, B, C, or D. And the hardest alloy is, yeah, B, martensite, definitely. We'll talk about why that is again by the end of this chapter. So now let's do our question for the beginning of class, which is, again, you had pure gold, and its melting point is 1064 Celsius, and you can supercool it 230 degrees Celsius below that temperature, which is the same as 230 degrees Kelvin, so we're talking about a difference, right? Calculate the critical nuclei size for homogeneous nucleation given the same values that we had last class. So again, you're going to use this R star equation. Remember, temperature needs to be in Kelvin. And then just note that that's joules per meters cubed and joules per meter squared.
Yeah, it's the
Okay, just another minute. Okay, get your answers in. We're going to wrap it up now. Okay, ending the poll. What answer do we get? I came up with 1.32. Looks like that's what the vast majority of people got. Okay, so any questions on this so far on these type of calculations with homogeneous nucleation? Okay, let's switch gears then. And let's talk about the rate of transformation, okay? Up until now, we've just been talking about nucleation, right? Which is just these things forming in the first place. But to transform, as you saw in the ice, right? When I hit that thing, you saw the little stars of like solid forming, and then they had to grow. So you have to have both phenomenon in order to get transformation. If you just crystallize a bunch of small nuclei but they never grow, you won't have a very fast transformation. So you have to have both growth or attachment of new molecules and atoms to it, as well as nucleation, right? So to calculate this, we do the following, right? First off, we need an expression that tells us the number of stable nuclei with respect to temperature, right? Stable nuclei, we'll call that N star, right? That's the number of nuclei that have R greater than R star at any given temperature. And the expression is given here, right? And it's the same format that we've seen a million times now in this class. It's a thermally activated process, right? You've got an exponential, a pre-exponential, and an exponential. So the pre-exponential, we'll just call it K1. That's going to be the number of single atoms that could potentially turn into a nuclei. You multiply that by the exponential of your negative activation energy for nucleation formation divided by kBt. So how is this different than every other thermally activated process we've seen so far in this class? What's the key difference? Maybe turn to your neighbor and discuss the key difference here. Okay, how is it different? Let me pick on Morgan. What do you think? It looks the same to you? Anybody see something that might be different here? Yeah, what do you think, Rob?
Well, we're usually given it in terms of, I think, of Q as our exponent. This is delta G.
Okay, and is it the same thing or different?
Well, Q, I don't know if is it a constant? I don't remember. Either way.
Q is a constant. That's exactly it. Q equals constant. So like if it's activation energy for vacancy formation or for diffusion or whatever, that was always a constant, right? At least over some temperature range, it was a constant. What do we know about delta G star? Is it constant with respect to temperature? Definitely not. In fact, we know how it depends with temperature, right? As you change temperature, the further below its melting point or whatever the transition temperature is that you go, it's changing. So this isn't exactly like the thermally activated processes we've come to know and love in this class. This has to be modified. This has a stronger temperature dependence, right? Because basically right there, it itself has T to the 1 over T squared in it, right? All right. So that's how we nucleate things. That gives us a way to calculate how many radii should exist as a function of temperature, right? If you knew what K1 was, that constant. Now we need to figure out the rate at which these things will grow, or the rate at which new atoms will come and attach themselves to it. So we call that V sub D, right? That's the frequency with which new atoms come and attach themselves to the surface. That one is our typical thermally activated process. V sub D equals now K2, some other constant, times the exponential of negative QD over kBt. And QD is our diffusion activation energy, right? So the same QD that we had when we modeled how fast carbon moves through a steel lattice, all those different things, you can look up what that activation energy is for your system, and that's how you're going to model growth, right? So with that said, you've got two factors, right? You have nucleation and growth. We need to take them both into account. So we do so as a function of temperature in a graphical way like this. So here we're going to plot, basically rate, right? This is really just saying the number of critical nuclei or the rate at which we attach new atoms, n star or v sub d. And here we're going to do temperature, right? You've got the temperature up here where you expect the transformation. This is T alpha beta. That's where you expect from a phase diagram for solid water to melt into liquid water, or for liquid water to solidify into solid ice, right? So as a function of temperature, the number of critical nuclei size should do the following. The lower you go in temperature, the more of them there should be, right? Because the lower and lower you go, the activation energy to form these nuclei gets smaller. Or in other words, the critical nuclei size gets smaller and smaller and smaller the further you go below that, right? Or in other words, we can't infinitely supercool this water. If we keep on supercooling it, eventually we're going to have so many nuclei, it's just going to crystallize, right? But on the other hand, that may not be the fastest way to crystallize it because we have to consider attachment. And attachment is going to mean that you need thermal energy for these water molecules to find their way to the ice crystal. And that does the opposite. It looks like, so I'm going to pick a different color, we do gray. V sub D, right there, that increases with temperature. It's a thermally activated process, right? So you've got these two things in competition with one another. And since you have to have both of them, we're going to multiply those two terms. And we're going to see that the overall rate of transformation does something like that. We'll call that N. N stars, or N dot is how they normally write it, right? So basically by multiplying the formation of nuclei and the growth of those nuclei, you get the overall transformation rate. Yeah?
Can you clarify why, so when you look at the map of the number of stable nuclei versus the map of solid nucleus, it's the exponent of an to log over t. Why is it that one is increasing and one is decreasing?
Good question. So if we were to plug all of that in right there, it changes the dependence. It's no longer an activation energy just divided by T. Now it's an activation energy divided by T squared, all that divided by T. So it has a fundamentally different temperature dependence, right? It goes the opposite way, essentially. Instead of getting bigger at higher temperatures, it's getting smaller. Okay. So again, if you want to see the math, you can just plug all of this guy into that, and you'd see that it actually has a different dependence. So again, the overall nucleation rate, N dot, that's the number of nuclei formed per volume per second. That is going to be A star, N star, V sub D. A star is the number of atoms on the surface. N star we've already talked about. V sub D we've already talked about. So again, that's going to be related to our transformation rate. Okay. So K1, K2, and K3, those are all just constants. Because they're constants, you can combine them into one constant, right? You could say that all these together, just call it K4, and there's just one of them, right? They're just constants. So you'll have a chance on one of these homeworks coming up to figure out what that constant is and calculate some of these numbers. Okay? Yeah, Josh? V sub D, that is right here. It's the frequency with which new atoms can diffuse to the surface, right? So diffusion rate, that's going to tell us the diffusion coefficient, that's the meter squared per second, right? That's diffusion coefficient. So it's going to be related to that. Okay? I think that's all we have to say here. I'll just remind you that everything we've done up till now has been for spherical, right? If you do any other shape that isn't spherical, if your crystal structure grows in like a structure that grows big cubic crystals, for example, or any other shape, you have to redo the math, but it's not so bad because the only place that comes into play is in the volume and the surface area equation. So if you go back up here, clear back up, you would modify this 4/3 pi r cubed, that's the volume of a sphere, and you'd modify the 4 pi r squared, that's the surface area of a sphere. And you do, instead of that, you do whatever other shape it's crystallizing in. Okay. That's homogeneous nucleation. Let's pivot now and talk about heterogeneous nucleation. How is this at all different? We mentioned it before. We basically said if this is your homogeneous nucleation, you had the alpha phase, and a beta nuclei forms in it. That's homogeneous nucleation. For heterogeneous nucleation, you had your big vat of, let's say, the alpha phase, but this time you've got an impurity, right? Let's draw something like this, right? You've got that impurity on there, and the beta phase is going to form on that impurity, and it won't form a perfect sphere because it's going to have a different wetting angle, right? If the wetting angle was like 180 degrees, it would form a perfect sphere on the surface, but it's not going to be that. It's going to be somewhere between 0 and 180 degrees. So it might form just like the cap of a sphere, right? Like that. And in doing so, it's going to change the ratio of the volume of this object to the surface area of the object, right? It's going to change it. So let's do the math here. Let's draw it up. So let's put an interface. So we've got something, right? This could be the side of the bottle. This could be a speck of dust. This could be just something. It's some sort of interface, right? And we've got solid forming on this, and we've got liquid out here. So it's all still molten. Here it's formed a solid. Here we're going to just call this interface. It's some sort of impurity, right? We can draw that the force is acting on this. We can say that there's a force right here. That's going to be the surface energy between the interface and the liquid. We have a force right here, which is going to be the surface energy between the solid and the liquid. And then you're going to have a surface energy right here, which will be the surface energy of the solid and the interface, right, or the impurity. Okay? You can sum these up and find that the in-plane force, right, in the x-plane could be solved by this expression, right, where this angle right here, this is your wetting angle right there. That's theta, what we call the wetting angle. Okay? So if you know the wetting angle, what that allows us to do is allows us to modify these expressions, and here's how it does so. Again, doing the math, you'll find that you get the exact same critical nuclei size. This is important. The critical nuclei size does not change, okay? But the activation energy does. The activation energy looks just like it did before, except it now has this additional term tacked onto it, S of theta. And S of theta, you can calculate it if you know the wetting angle. And the point is that it's always going to be a number between 0 and 1. Therefore, if you take what we had before was the homogeneous activation energy, this part right here, you're taking that number and you're multiplying it by something between 0 and 1. That means that the activation energy can only ever go down for heterogeneous nucleation. It can only be smaller, right? The size, the critical nuclei size does not change, but the barrier does change. So graphically, what does that look like? That looks like this, right? Here's our homogeneous case. Right, that's homogeneous. So it had some point r star, and it had some height over here. We call this distance right there delta g star for homogeneous, right? Now we're modifying that, and we're going to have the same r star, but we're going to have something smaller in terms of activation energy. So it might look something like this, right? So that distance right there, that is that guy. Any questions? Yeah.
What was your theta?
Theta, in the droplet, when your droplet forms on the side of the bottle, on the speck of dust, whatever it is, theta is this angle right here. You basically look at that steepest angle right here and look at it going up. Actually, let me show you this. This is kind of neat. Yeah, let me show you real quick. Okay, so here we go. So this is from the guy who detects angle pretty accurately. So all it is, it's a camera that's going to look at the side of your interface and the droplet on it, and you're going to make a very careful photograph of it, and then you're going to figure out what that angle is, right? From that angle, you can do, so this is water, you've got, oil on that. You're going to have different angles because materials have different levels of what we call hydrophobicity or hydrophilicity, right? You can have a hydrophobic material where it's going to beat up on it, or a hydrophilic material where it's going to try and smooth out across it. So this is a relatively easy thing to measure, and if you know it, then you can figure out how much of an energy reduction you're going to see in terms of your heterogeneous activation energy. Okay. Any questions so far? Yeah.
It's not tangent to the sphere.
Kind of, yeah, it is. It's the point tangent between the point where the droplet touches the surface. It's that angle that it immediately leaves with. So you could say it's the derivative of that tangent, I guess. right, as it approaches the interface. Okay? Yeah, Rob?
So between heterogeneous and homogeneous, it has the same R star.
They have the same critical radii size. That's really important, but they have different activation energies. Natalia?
So formula for S is going to be the same for different geometry?
So it depends on geometry by incorporating theta right there. Oh, I see. If you have like a cubic one or something, yeah, this is only for spherical. So I don't have the expression for something non-spherical. And all this is this is just telling you the surface area basically of that nuclei of the cap. So if you have a sphere here and you were to chop it, it's basically telling you just this part of the sphere. That's all that formula is doing. It's the spherical cap. Okay? And, in older editions of the book, it was there, and I think on the third edition, I don't know if it's actually there. So this is just in the notes, that one. Okay? Again, just to reiterate this point, your activation energy for heterogeneous will be equal to your homogeneous activation energy multiplied by some number between 0 and 1. So it's just going to reduce it. Okay? Okay, so how does this compare? How do your rates compare? If we plot this like we did before, we're now going to plot as a function of temperature. Here's the temperature where we expected things to happen, T alpha beta, and this is going to be, say, rate, n dot. That's our rate of nucleation. For homogeneous nucleation, it looked like this. How is it going to look differently for heterogeneous nucleation? Maybe turn to your neighbor and discuss how might it look different. Okay, what do you guys think? Does anybody want to volunteer a guess? What do we know? And based off of what we know about heterogeneous versus homogeneous nucleation, how should it look? Yeah, what do you think, Rob?
It should be a much higher.
It should be a higher rate, or if it's the same rate, should that happen at a higher or lower temperature? Closer to the transition point or further away from it? Closer. Yeah, you'd expect maybe this. Or in other words, if you have heterogeneous nucleation conditions, you won't be able to supercool it as much, right? Because there's less of an energy barrier. The energy barrier just gets cut off. So your rate is going to be faster at smaller delta T's away from your melting point. Okay? Okay, technically we've talked about attachment rates, so the rate at which these things grow. There is a full expression for growth. It basically looks the exact same as V sub D, right? You've got some constant times your diffusion coefficient. So in the book, they actually show this separately. They show it look like this. Again, plotting as a function of temperature. You've got the temperature where you expect it to happen. They show that your nucleation rate is down here, and with a dot. And then they show growth as being something higher, where you get maximum growth up here. And so for your overall transformation rate, this is the one that matters, you get this N shape, this cone, they call it a nose-shaped curve, right? Nose-shaped curve, right? Because you're multiplying your growth by your nucleation rate, okay? And this is maybe intuitive. What this means is that as you're below your melting transition point, the point where you expected it to happen, there's some temperature right here where you get the fastest rate. That's your fastest rate of transformation. Or in other words, if you go just a little bit below the melting point, it's not going to transform very quickly. And if you quench it really aggressively down to, say, room temperature or really low temperatures, it's not going to transform quickly either because you won't have enough energy for these things to grow. So because of that, you can actually quench phases and make them metastable, right? You could quench it, you could drop it so quick down in temperature here that your rate of transformation, the blue curve there, your nose-shaped curve, is essentially zero, meaning it's not transforming at all. So the metal alloys that we brought into class, that's basically what we did there. We quenched them into ice water, and they weren't transforming at all quickly until we held on to it in our hand, and we brought it up in temperature somewhere around here where it had an appreciable rate of transformation. Okay? Any questions so far on this? Nucleation versus growth. Yeah, Rosa?
Why is heterogeneous nucleation, why does it happen slower at the same temperature than homogeneous?
It should happen faster. Well, the rate should look like this. At temperatures close to the transition point, it should be way faster than homogeneous, right? But when you go down in temperature, you now have passed the point where diffusion, basically, it just like before, you've got this playoff between attachment rates and number of nuclei. So you might have lots and lots of nuclei down at low temperatures, but you're going to have a lower attachment rate. Yeah, question, Elise?
Would you be able to do the same thing with martensite?
Yeah, we'll talk about martensite in just a minute. Martensite, that's a perfect example of basically quenching it so fast that you never are in the region of this nose where it is going to transform. So you quench a high temperature phase down to room temperature.
But would you be able to give it some activation energy?
We're going to talk about that. You absolutely can. Yeah, you can go from martensite back into some of these other steels. They call it tempered martensite. And it's one of the better grades of steel out there because it has a mix of both properties. It has good hardness, but it has some significant ductility. Yeah, Jeff?
Sorry, can you tell me one more time what the red curve there is?
So the red curve, that's growth. Let me mark that. Which is that thing, right? So you've got your nucleation rate and your growth rate. It's a bit tricky because nucleation rate included an attachment rate, which is kind of like growth, right? But that's these things taken together. Now, if this is the rate, this blue curve, that nose-shaped curve, that represents rate, right? What do we know about rate and time until completion? We know that they're inversely related, right? Time till completion is going to be inversely proportional to the rate, right? So the rate of its transformation is really fast, then the time till completion is going to be very small, right? So because of that, this comes to the final plot that we need to talk about, which is the TTT curves. This is how they look. You're going to plot temperature up here and time down here. And basically what you see is a series of what are called C curves. Grab and move this thing. Right? So you've got a series of TTT. On the TTT diagram, you have a series of these C-shaped curves, and they'll normally draw them like this with solid lines and a dashed line. The solid line represents 0% transformed. This solid line over here represents 100% transformed. And this one would be 50%, right? So what this shows you is, let's say that you could somehow magically change the temperature of your alloy instantaneously. We'll learn later that that's not possible. It always takes some amount of time to change its temperature. But if you could change its temperature instantaneously, let's say that the transformation temperature is up there somewhere, but you instantly bring it down to this temperature, you could wait some period of time before any transformation occurs, right? But as soon as you touch the nose, right, of that TTT diagram, that's when your first transformation starts to take place. And then the longer you hold it there, you hold it all the way up to here, by the time you get to this time, whatever that is, then your transformation is going to be complete. This is typically plotted on a log scale, so this is log of time down there. And they'll call these TTT curves because it's time, temperature, and transformation, right? Time, temperature, transformation, so TTT curves. We'll come back to that when we talk about steel quite a bit later this chapter. Any questions on it so far? Yeah, Haley? Yeah, good question. You could do the time till any point. Time 0.5, that means the time for it to reach halfway completion right there. So basically they are solving for the time to get to that point. But you could have time 100%, time 0%. You could solve for any of those you wanted. So it doesn't have to be 0.5. So I've left it off for that reason. Okay? Any questions? Yeah, Rosa?
Is this assuming you're at like a eutectoid composition?
Great question. We will show you what happens when you're at the eutectoid composition versus off of it in just a minute. That's a really good question. Okay, let's before we talk about steel, let's talk about microstructures that form quickly. When you melt something, if you take molten, say, aluminum or whatever else, maybe you've seen this before, but if you melt it and then you cool it down, maybe the first thing you notice is that it's got like this little dip in the top, right? So it's going to shrink oftentimes as it cools down, and so you'll see this divot forming from this shrinking, right? That's the first thing you'll notice. And then if you were to cut that thing open and polish it, you'll notice that the microstructure is also changing, right? You have a bunch of really tiny grains here at the very edge. Then you've got these long grains in the middle region, and then you've got equiaxed, they're not sort of stretching in any one direction in the middle, right? This happens because you have a temperature gradient across your sample as it's cooling down, right? So you see lots of nucleation happening at these edges. How come? Why do you see tons of nucleation right at the edge of the mold? Because it's cold, right? If we go back to our drawings, right, we showed nucleation, the number of nuclei as a function of temperature. If you're way below the melting temperature, you should have tons of nuclei, right? So it's going to have lots and lots of little nuclei at the edge that are going to form. And then as you go deeper within the alloy as it's cooling down, you're at a higher temperature where growth is going to dominate. So because of that, you'll see lots of grains at the edge, but some of these will grow more than others as you go towards warmer and warmer regions. And they're going to tend to grow in the temperature of the temperature gradient. Yeah, question?
It's just a general question about the graph, but why is temperature on the y-axis? Because it seems like all of the graphs aren't functions. It seems like they're...
Oh, yeah. They're trying to show you the amount of something. Sometimes that's a rate, sometimes that's number of something. But it's all happening with respect to a degree of supercooling. So in the chapter, when they teach this, it's all about starting with a molten metal and turning it into an alloy. So they're talking about going down in temperature. So I think they graphically chose to do it that way. You could plot out reversed though. Absolutely, yeah. You could invert it. I think that they thought it was simpler to do it that way. And I'm just using what they did. Question, Rob?
This is why Prince Rupert drops work the way they do, right?
Yeah, we'll come back to Prince Rupert droplets. Yeah, we won't cover those right now. Any other questions about this? Okay, let's keep going. One other thing to know is that this is one type of microstructure. Another very common type of microstructure can exist, and it's called the dendritic structure, and it's pretty cool how it works. So let's show you the two examples. So this is from Cambridge. They've got a great little flash tutorial on it. So you've got two scenarios. Here's your first one. So on the right-hand side, this is the liquid. This is your alloy. On the left-hand side, this would be like the container, right? So as you start to solidify, your solid's going to form near the container, right? If your temperature of your liquid is much hotter than your container, then as you do this, something might solidify, but the rest of it's going to catch up. So these perturbations at the surface keep on getting swallowed up. And so it's going to look like just the alloy that we just saw. You can have another scenario. If your mold is at such a high temperature that it's really close to the temperature of your liquid, and then your material, let's say, absorbs energy as it solidifies, which is not uncommon, it changes this scenario. Now, let's say that some sort of perturbance forms, right? Some little bit of it from the liquid phase, it forms a little bit of a solid right here first. Well, in doing so, what that does, let's go to our next one. That's going to lower the temperature even more of the liquid nearby it. So that's going to cause this thing to grow out into the liquid, right? So they'll call this branch instability, where basically it has a driving force for it to keep on growing out because we're basically, the tip where it's growing is at a temperature that's lower. So it's going to keep on solidifying at the tip first. And so it grows these weird kind of Christmas tree looking things. And that is the dendritic structure, right? So you'll see this all the time in metal alloys. It's very, very common. And you'll wonder where on earth is that coming from? It has to do with the temperature upon cooling this alloy down, okay? That is different than snowflakes. Snowflakes grow the way they do for a different reason. So again, you've got air out here and you've got solid. In the air, you've got little water molecules, right? You've got these water molecules. And if you have a protuberance, right, some sort of imperfection where it sticks out a little bit further, the water molecules in air, they have to diffuse a shorter distance here and a longer distance there. So they're going to grow at the end of this thing. It's going to keep on growing longer. If it has protuberance, they're going to grow longer, and you get this snowflake sort of structure. Okay? Yeah, question?
In the dendritic structure, how come it doesn't just sort of grow as a pyramid, like as a moving front, rather like why does it form those branches?
Because
like regular animals?
The branches form let's go back. So do this one, right? Some tiny imperfection formed here. right? And then that thing's going to grow, but imperfections can form on the side of that as well. And they'll extend out, and they're going to grow for the exact same reason.
So it's not really like regular intervals, it's just kind of whatever happens.
You'll see that it does kind of have somewhat regular intervals. Okay? We are out of time, so we'll pick up here next time on Avrami kinetics and finish up this chapter. Quick note, I've posted homework 9, and it is a team project. So it is a presentation. You're going to have to make a 5-minute PowerPoint presentation and pre-record yourselves talking on it. So groups of, I think it's 4 to 6 people, check the announcement. Make sure that it's the exact right amount of time. It has to be on a kinetic topic, so we'll talk more about it on Friday, but do take a look at that. That's already posted.